recording is rolling. So it's Monday, May 9th. We've got these real short class periods. So we're gonna do a little activity here. You guys get to learn something about nature. All right, you guys just watched most of this video, number file, the golden ratio, why it is so irrational. And so here's what I'm about to do. I'm gonna throw something from a little bit different point of view, then I'll work backwards and work back to the starter question about that video. So do you guys know something called the Fibonacci sequence? I bet a lot of you guys do. What is that? How does it go? There's a certain pattern, right? Go right. So it's this sequence of numbers. Right? You need to start with 0 and 1 or 1 and 1. Right? And then what do? You add them.
Yeah.
Exactly. So 1 and 1 makes 2. Okay. And you always add the previous 2 together. 1 and 2 is 3. 3 and 2 is 5. 3 and 5 is 8. 8 and 5 is 13. I'll do a few more. 8 and 13 is like 21. 13 and 21 is 34. Those two together, it's 55. Those two together, that's 89. Okay. You can go on forever, right? Yeah. Right. Now, something kind of funny. If you take the ratio of any two of these numbers, especially the larger ones, it actually approximates a certain number. So let's try this out. Like, what is 89 over 55, for example? 89 over 55. Right? That's 1.618 and change. Huh. Okay. Does anybody recognize what constant that is in nature? That right there is called a lot of times designated Greek letter phi. So it's phi to represent kind of like pi. It's just it represents 3.14 most often. Okay, so that is called the golden ratio, okay. And it's what ratio? Okay. It's irrational, but it's approximately equal to 1.618. Kind of like saying pi is approximately 3.14, but you're chopping off all those little tiny digits, right? And so this is irrational. Okay. You see this ratio all over the place in nature and architecture. In fact, if you have a rectangle that is like these dimensions, like for example, an 8x5 rectangle, that's called a golden rectangle. Like anything that pretty much has proportions that are pretty close to this. Right? There's different things you can optimize. In fact, that's kind of where we're headed with the story. So that video I had you guys watch says, why is it so irrational? It's actually considered to be the most irrational number. Right? And the first part of the video I played for you guys, he went through that proof and showed you guys with a continued fraction why that's the case, like from that perspective. Okay? He was saying, well, pi actually is not very irrational. There's some numbers that are more irrational. This number, if you go through the continued fraction, is actually the most irrational. You can set up an equation and solve this. It goes like this: x minus 1 is equal to 1 over x. Okay? If you go solve that, you get the solution. X is equal to 1, well, it's plus or minus 3.5. You just call it like plus 3.5 over 2, right? Which again comes out to about 1.618. Okay. All right, so what does this have to do with, at the very beginning of the video, he's doing something like sunflowers or something. Right, let me flip the screen over and show you guys a picture of a sunflower. All right, ooh, look at that. Yeah, you guys see those seeds in a like spiral type pattern? Right, now there's a connection here. And it has to do with well, evolutionary biology. Suppose it's like, I don't know, 10 million, 100 million years ago, like sometime in the deep, deep past. Maybe there were different kinds of sunflowers that had like different like genetic codes that made them sprout like different patterns, right? Well, if there were some sunflowers, and this isn't just sunflowers, this is a whole host of plants that we're about to get to, that had like a non-optimal layout of seeds or flower petals or leaves, then they would either not be able to pack as many seeds, or the leaves wouldn't capture as much light, or maybe the flower area would not attract as many bees. Okay. And so the result would be that their genetic code wouldn't be as good. And if you had, say, one that had like a really good spiral pattern that either packed the most seeds per area or exposed the most amount of leaf to capture the most amount of sunlight, or had like the most amount of flower petal available, so the bees could be like, hey, there's a flower over there. Okay. They're going to be more likely to do well in life and pass on their genetic code. Okay? So we don't draw anything quite yet, but we give you guys sort of a counterexample of maybe some genetic code that would have been lost to nature because it just wouldn't be very good. Okay? Let's say you're a plant, you have some genetic code that says to sprout, maybe with petals, but you could do seeds or leaves or whatever story you want to go with. Okay. Do like petals, right? And let's say we're going to put one petal out right here. And then maybe every so many degrees, I'll sprout another petal. We're going to go like a spiral pattern, right? Okay. So, just to come up with something, let's say every 90 degrees, right? So every 90 degrees, I'll sprout a new place for a petal. I'll go back and draw them later. So 90 degrees, that's up here, boom, 90 degrees from that, boom, and then 90 degrees from that point, boom, right? So gotta put a petal in that direction, petal in that direction, petal in that direction. Okay, so far this is looking good. Okay, here, I'll even draw on the petals where they go. Say there was like one here, oops, one here. You can draw these whatever shape you want, but it's kind of something. Okay, so everything's all fine and good, blah, blah, blah. Right. And then if you pick up from this one and turn another 90 degrees, oh boy, does that land you exactly on top of the first petal? It sure does, which would be probably not a good design, right? Because now the first petal is completely ineffectual, right? If these were leaves, it would be covering up a leaf. It could no longer capture sunlight, right? Right. Okay. So this is not a very good design. Right? Now, how could I get 90 degrees? Could I take 360 degrees in the circle and divide by 4, and that could give me to 90 degrees, right? You can think of it that way. But then you could pick any integer, and you're going to run into the same problem. I could do 360 degrees divided by 5, and that looks good for the first 5. But then the sixth petal would exactly cover the first one. Any integer, you're going to run into that problem, aren't you? So this is why you don't want to take 360 degrees and divide it by an integer. You want to divide by an irrational number. Okay, so then just randomly different plant genetic codes land on different, probably irrational numbers for something like this. Right? Go look out in the world, lots of flowers, pine cones, like leaves on vines. You'll see spirals all over the places on plants. Okay? But I bet if there were some numbers that were like more irrational than other numbers, they'd probably give a slightly better design, right? And then over time, fast forward millions of years, like that would be the design that would stick around nature because it was just most successful. That's why probably the most irrational number, like in this case 5, this golden ratio, is going to win out over all the other ones. So let's do some calculation here. What if I take 360 degrees and I divide by this golden ratio? I'm going to round it a little bit to 1.618. Of course, it's irrational, so it goes on forever. I wonder what this is going to give me. What's the optimal turn angle? And the answer is about 222.5 degrees. Right? That'd be plenty good, plenty of precise for what we're about to do. Okay? But you know what? That is more than 180 degrees. So if you said like 222 clockwise, would that be the same thing as you go counterclockwise, a shorter angle turn? Okay. Maybe I should do this. Maybe I should take 360 degrees and subtract 222.5 because it would be like the same angle, just counterclockwise instead of clockwise sort of deal. Okay, let's take 360 minus that. And that gives me 137.5 degrees, which is just easier to measure with a protractor. Okay. So we're going to use that as like the optimal angle. Right? Right, so here's where you guys get to do something. Right, so put a dot in the middle of your paper. Right, you guys got a dot down? Right, you guys got a protractor? Does anybody not have a protractor? Right. Oh, okay. Everybody right? There's probably a spare one up here. All right, there might be some extra ones around like lab tables. Okay. Right, so mark out a location for the very first petal. Okay. And then we're going to turn 137.5 degrees. Right, so let's go. Maybe I'm going to go clockwise with the. Okay, I think that'll work out. Clockwise. It doesn't matter either way. 137.5, boom, right there. And that will be the location of the second petal. Okay. Now, maybe in theory, you could stop this process whenever, but I see a huge gap here, huge opportunity for more petals. So I'm going to pick up from that point here. Here's what we did so far. 137 degrees. This was my first petal. This is my second petal. Right. I'm going to just pick up from the second petal, zero that out, and sweep out another 137.5 degrees. Land me right here. That's petal number 3, 137.5 degrees. 0.5 degrees. I'm going to pick up from the third petal, zero that one out, and sweep out another 137.5 degrees. Right there. Boom. So this angle here is 137.5 degrees. This is my fourth petal. Okay. Now, if you stopped right here, would there be a huge gap just like begging for another petal? Looks like it. So let's throw at least one more down. Okay, so zero out the number 4, petal number 4, sweep out 137.5, boom, right here. That'd be a good spot. That's another 137.5 degrees. That's your fifth petal right there. Okay. Now, if you step back and look at that, does that look pretty well balanced at this point? Pretty well balanced? I think so. And you know what? Five petals. Do you see a lot of flowers in nature with 5 petals? Yeah. What if I hadn't put this fifth one on here, like 4? Let's think about clovers for a minute. Guys, how many 4-leaf clovers are there? Is that a really common or is that very rare? Very rare to get 4-leaf clover. Probably because it's not the most optimal way for plants to grow. Oh, you know what else? Take a look at this Fibonacci sequence from a few minutes back. 4 is not a Fibonacci number, but 5 is. That's kind of interesting. In fact, if you go out just in nature, find a bunch of pine cones or flowers or this or that, and you count like how many petals are on these flowers. Say you found a flower like a bunch of petals on it. There's actually a really good chance it's going to be one of these here Fibonacci numbers. Like oh, hey, there's totally 55 on this. Yeah, no, but maybe go try it out. It's good. Okay, so we're going to finish this off here. So I've got spokes where the petals would go. So last thing I'm going to do is just draw in some petals. You can pick whatever design you want. I'm just going to pick up something. So this is like the artistic part of this. Okay, just use your imagination, draw a petal. I'm going to make this radially symmetric. So it's just like I'm taking the same shape and just rotating it around. Trying to do my best. Something like that. Look at that. Looks like a pretty good flower. Pretty good. Looks pretty well balanced. Right? It's got an optimal angle in it. Right? You know what I want to say about this this golden ratio, right? Because I mentioned for flowers, you see this all the time in a bunch of plants too, right? Plants, flowers, anything that's spirally. Take a look. You'll oftentimes see this angle, right, which comes from this. Mention the golden rectangle and architecture you see all over the place because it looks like pretty well balanced, like 8 by 5 or pretty close to it. You know where else you see this proportion, this golden ratio proportion, is in you. For example, if you go from your elbow to the tip of your finger, and you go just your forearm, take that ratio. That's a 1.618 ratio. All right, so I'll give you guys points for this activity. You don't have to share anything in. So I'll just put in posts behind the scene. You guys have a great rest of your day. Hope you guys enjoyed.